The next few sensors have to do with the phone's physical location in space. The accelerometer was talked about by Steve Jobs as the sensor that determines whether your phone is in landscape or portrait mode. How does it do that if it's just measuring acceleration? Well, most phones will have at least a two-axis accelerometer, which essentially means that you have two accelerometers placed at a 90-degree angle to each other. One axis aligns with the height of your phone. You can think of it as the portrait axis. And the other axis aligns with the width of your phone. That's the landscape axis. When you're holding the phone perfectly still in portrait mode, the acceleration on the portrait axis will register 9.8 meters per second squared, which is the acceleration upwards, yes, I said upwards, due to the fact that you are resisting the pull of Earth's gravity. The acceleration along the landscape axis is 0. If you rotate the phone to portrait mode, the measurements along these axes will flip. If you drop the phone, then while the phone is in free fall, the measurements along both axes will be 0. Laptops with hard disks often use free-fall accelerometers that are dedicated to determining if the laptop is falling. If the computer is falling, it quickly parks the head of the drive to minimize the chance of data loss from the head hitting the platter. If you have your phone mounted on the dashboard of your car so that you can look at it, and you want the accelerometer to register how fast you're accelerating the car, you need a 3-axis accelerometer, one that not only detects acceleration along the portrait and landscape axes, but can also detect acceleration along the axis that corresponds to the thickness of your phone. Now, most phones made today will use 3-axis accelerometers so that they can capture movement along all 3 spatial dimensions. In addition to detecting screen orientation, accelerometers can be used by pedometer applications to detect how many steps you take. They can also be used by gaming applications to gather input on how you're moving your phone through space. And they can also be used by your phone's camera to minimize the blur in a picture when your hands are shaking. To really get precise information about how your phone is moving through 3-dimensional space, the data coming from the accelerometer needs to be paired with the data coming from your phone's gyroscope. The accelerometer tells you how your phone is moving along the 3 linear dimensions. The gyroscope tells you how your phone is rotating along those 3 dimensions. In aviation, these rotations are known as roll, pitch, and yaw. When you play a racing game on your phone and tilt the screen to steer, it's the gyroscope, not the accelerometer, that's sensing your movement. Accelerometers are good at detecting broad movements through space, but to detect those subtle rotations, you really need a gyroscope. When you combine a gyroscope with a 3-axis accelerometer, you end up with a full 6-degree of freedom sensor known as an inertial measurement unit, or IMU. In addition to 3 accelerometers and 3 gyroscopes, many IMUs will also contain 3 magnetometers, which are sensors that detect magnetic fields. We'll talk about those in the next slide. IMUs are used to help operate aircraft and drones and rockets, but they can also be used in your phone to help you navigate when you're out of range of the GPS, like when you're going through a tunnel or when you're in a big city surrounded by tall buildings. Accelerometers and gyroscopes are also used in gaming input devices like Wii controllers, in digital cameras, including your phone's camera, to help with image stabilization, in cars for collision detection, and in machinery to monitor when equipment is behaving erratically. The accelerometer and gyroscope sensors are so sensitive in modern phones that if somebody can eavesdrop on the data coming from these sensors, they can actually determine which keys you're hitting when you're entering a PIN or a password. The final sensor related to detecting spatial changes in your phone is a magnetometer. The most common use for a magnetometer is as a compass. It tells you what direction you're headed relative to the Earth's magnetic field. Like accelerometers and gyroscopes, you'll typically have 3 magnetometers in your phone so that you can tell which direction you're headed in regardless of how your phone is oriented. Note that magnetometers are not just good for acting like a compass, they detect magnetic fields in general. So magnetometers are also found in metal detectors. In fact, believe it or not, you can even get metal detector applications for your phone that utilize its magnetometer. The GPS receiver on your phone gets information from multiple satellites, usually you need at least 3, and uses that data to calculate its location on the Earth. GPS satellites are owned by the U.S. government and operated by the U.S. Air Force. Europe, Russia, and China have their own navigation systems. The GPS unit in your phone is just a receiver. It does not transmit any information back to the satellites. GPS is considered to be hard on your phone's battery life, and there are a couple reasons for this. GPS signals have very low bandwidth, so the receiver has to be on longer to get all the information. And as we've already said, it has to receive data from multiple satellites. But it's also the case that applications that use GPS, like your navigation system, for example, tend to be power hungry. They're continually accessing information from the GPS, asking it for more, and even communicating with cell phone towers to get map data and information about the area that you're driving through. Now, even with your phone's accelerometers, gyroscopes, and magnetometers, the GPS is still your critical navigation device. That's because those sensors we mentioned are always going to be subject to a certain amount of drift. So if you're navigating in a city with a lot of big buildings that interfere with your GPS signal, your phone is going to try to estimate where you are. But if it's away from the signal for a while, it's eventually going to drift away from your real location. Once you get the GPS signal back, it'll quickly reset your correct location.